Should. Okay, so this is going to be our report, a report on our joint work with Nalin Vishwas and Chandra Maiti. And the basic question that we consider is if G is a Lie group and H a closed subgroup, we want to obtain some computable expression for the Deram cohomology of G mod H for at least, I mean, we have done the work for 1, 2, 3, 4. I'm going to explain what do I mean by computable by giving some examples. I cannot exactly say what it means, but I'll give some examples through which it will be clear what I want to mean. And we'll begin by describing our motivation, how we came to this point about asking this question. So, so this is a remarkable fact about Lie group is if I take a Lie group G, Lie group, and G, the Lie algebra, then I have this G dual, this the linear functionals. This is a real Lie group. Then G acts on G dual by the joint representation. So lambda, let's say lambda G dual, then G in G, and G lambda I define to be lambda compose add inverse. So we consider the orbits. So we consider the orbits of this it's a remarkable fact that these orbits are associated with a natural symplectic form. So which is called, I'm going to define it. And so these orbits are, of course, I mean, not going to be embedded submanifold. So this, as a set, it lies inside this, but need not be an embedded submanifold. So I prefer to deal these orbits by identifying with the stabilizer where G lambda is the I'll identify these objects with this, and these objects, these orbits acquire a natural symplectic form. So now, and I am coming to know that this is also form. But since I made the slide with these two names, I'll continue this. But this name is also relevant to this construction. So let's take two elements in the Lie algebra G, and I have this gamma x. And pick a point as before in G, and it's G lambda. Here it's just a coset of a point in G by G lambda, left coset. So I'm going to define the fundamental vector. I consider the fundamental vector field. So G has a natural left action on this coset space G by G lambda, and we have this corresponding to this x. I have the fundamental vector field for which the integral curve is defined by, let's say, x X. And similarly, I define Y. And then one defines the two form, let's call it from the so this I take the derivative G lambda Z. Yeah, maybe I'll write to the other side, is it? Yeah, it's maybe I'll finish writing this. If I write and lose time. So this is defined to be lambda at G inverse of xy. And yeah, if you write in terms of the orbit directly, you can also write in a much more simplified fashion, but I always want to consider these orbits as this coset space, precisely because these are not embedded submanifolds. So this is, one can check that this form, this two form is well, this definition is well defined, non-degenerate, closed, and G invariant. G invariance will give the smoothness of the form also. So this is called the Kirillov-Kostantsovry form, and we wanted to check the exactness of this form. So we wanted to check the exact. So basically, this is happening in a general Lie group. So it's a remarkable fact that this comes with this form and this coadjoint orbital symplectic structure in particular. These are even dimensional manifolds. So it's a natural question to ask when this form is exact. And if the G happens to be a semisimple Lie group, so then via the killing form, the orbits, the coadjoint orbits are G equivalently isomorphic to adjoint orbits. So these can transport the symplectic structure to adjoint orbits when G is a semisimple Lie group. So all the if you take a semisimple Lie group, if you take the adjoint orbits, then these are also comes with this symplectic structure. So one would like to know when these forms are closed. Exact. Okay, so and some time back we have given some So this is our first motivation. So yeah. Huh? Oh, sorry. Yeah, you're right. Sorry. Yeah. Thank you. So we gave an exactness criteria for this KK form, KKS form for a class of semisimple Lie groups based on the eigenvalues of the operator add x. So you take a x and you take the orbit of x in the Lie algebra, G, take the adjoint orbit, and then you consider the add x. Add x will have eigenvalues. So based on the eigenvalues, we gave an exactness criteria. So some time back we did this work with Andrei. And then this work leads. So this since this form is a closed form, and so it induces a second cohomology class. So this question of computing the full second cohomology class for this orbits came naturally to us. But then we looked at the literature to see that whether we can get a clean formula for expressing second cohomology groups when we have a homogeneous space of the form G mod H. But it was not there, so we started looking at the problem of getting a formula for this de Rham cohomology groups since that point. Okay. So here is the question. So can you give a description of the second cohomology of such orbits? And of course, more generally, can you give a formula for the second cohomology groups for G mod H in terms of Lie theoretic data, GH, this, and how H is positioned inside G? And so the problem, of course, I'll talk about how much we know or what are the classical results that we know and what is our work. But the first beginning step is the following theorem of due to Mostow, which says that if we have a connected Lie group and M a closed subgroup with finitely many connected components, and G a maximal compact subgroup of L, and suppose that G intersection M is a maximal compact subgroup of M, then this G mod H sits inside L mod M as an embedded submanifold, and not just that, it's going to be a deformation retract of L mod M. So the problem of in the general Lie group setting boils down to the setting of compact homogeneous spaces, and this is what this is the first step. So then we have this by direct method we have a clean description of this second cohomology group which we have proved, and we have in fact used this. So this is some time back, and so it involves. You see that this results involve how H is. So yeah, it is depicted in terms of the maximal compact subgroup, but it is really a theorem of for a compact group and a closed subgroup. So you can ignore L mod M. You can simply write G mod H. So you see this. So this object is the center of the Lie algebra of H, and you know the commutator how it intersects, and H is acting by adjoint on this object, and you take the fixed point set, and H naught is fixing ZH, so it is acting through the finite group H by H naught. So this is really how H is center of H is positioned with respect to this, and these are the objects that are required. And if you in addition assume semi-simplicity of G or H, then you can get stronger results. So, and we have used this result to compute second cohomology group of nilpotent orbits in this complex semi-simple Lie algebras, and we have this vanishing result. So if you take all this exceptional sp2n and so on, and you get such a result. So this is using a previous version of the result that we just now did. So also you can use it for the real semi-simple Lie algebras, which is more subtle than the complex ones. And if you don't, I have to explain all these things. So these are basically nilpotent orbits, and nilpotent orbits are parameterized using certain diagrams, and you can get precise description of the second cohomology groups in terms of those parameterizations. So using this result. So, and now, so the next question naturally comes to us is, we have given the description for H2. What can you do it for higher cohomologies like H3, H4, and so on? So, but complexity increases as you go up. So let us, I mean, so there are some general facts which we will not go into. So these are generalities which are kind of classical. So if you want to, it all follows from a connected Lie group, connected compact Lie group is acting on a manifold, then the cohomology of the manifold is the cohomology of the G invariant forms. And these are all classical. So let's not go into that. But you cannot do much with these classical results apart from when it comes to computing, in a given situation, you cannot do much. So so I'm going to state our results for 3 and 4, but before that, let us just say what exactly I mean by computable. So this will, in a specific situation, you are given a group G and H, whether you can compute or not. So here are the classical results by Borel. So you see that if G is a compact connected Lie group and H is a closed subgroup, suppose that we have a equirank case, rank of G is same as that of H, and the cohomology of G is exterior around the primitive forms and so on. And then the Poincare polynomial, which gives the Betti numbers, it's given by an exact formula like this. And this is what I mean by computable results. So this degree of X so if you have in a simple group situation, all these degrees are very well known, even for exceptional groups. They're all classical results. So if you are in a particular situation, you can really compute this. But this is in a very, this is a fantastic result, but it also assumes this is a very strong condition. And you know what maximal rank subgroups appear, how it appears using Borel-Lewenthal. And so here is a result, here an example of a result which which gives, which gives the feeling what I mean by computable. So, but there are some serious restriction of this also. But then there is another beautiful result by Hopf, Samuelson. These are quite classical result by Wang. So if you take the Euler characteristic suppose G is a compact Lie group, H is a subgroup, and the rank of G is higher than that of H, then the Euler characteristic is 0. And if and only if, in fact, if the rank is equal, then you have an exact formula for the Euler characteristic. And this is another computable result. So you take the while group. So if the rank is equal, then if I fix a maximal torus inside H, that remains that also going to be a maximal torus inside G. So the while group of H sits inside while group of G. So the number of elements in while group of H divides the number of elements of while group of G, and the Euler characteristic is given by exactly by this quotient. So here is another example of a result which is computable. Yeah, so let's now describe a computable formula for H3 and H4 that we have obtained. So here are the bilinear forms, symmetric bilinear forms on. I take a Lie group G, compact Lie group G, take the commutator, take the symmetric bilinear forms on the commutator, and take the G invariant bilinear form, and you intersect with H. And so, of course, the restriction gives a H invariant bilinear form. And let's denote this restriction by GH phi. This is the restriction. So I need this notation. And here is this is the kernel. NGH is the kernel, and CGH is the co-kernel because it involves H. And I'm not assuming H to be connected here. H can be disconnected. Then we have this formula for H3, which says that you can pinpoint the third cohomology of this, and then we have the fourth cohomology, description of the fourth cohomology. So you see, if you G, E, and H are in a special setting, G and H are semi-simple, then you can really get stronger results. This gives the precise formula for this, and this is a computable formula. So by the way, this I should also say, I should go back to Borel's result, and I should point out one fact that you see, when the case is equirank case, then this formula for given by Borel, it says that it doesn't depend, the Betti numbers doesn't depend on how H is positioned inside G. It just depends on how it's the isomorphism class of H. Okay, so you just take something H which is isomorphic, H1 isomorphic to H2, then in the equirank case you have the same Betti numbers. But that's not going to be the case in here in a general setting. So this is something general. H is G is any compact connected Lie group, and H is closed subgroup. Then we have this formula, and you see how H is. It depends on how H is positioned inside H. So G. So, and you have this. If you can draw a lot of corollaries from this. And you see, I would like to mention the last thing that this one. So, if I have in a semisimple setting, if both are semisimple, then the H4 minus H3 is, so let me is number of simple factors of H minus number of simple factors of G. And this is something easily computable if you are given a special situation. So here we have, so if you have a compact semisimple Lie group and two Lie groups and H subgroups, and suppose H1, the number of this difference of simple factors in G and H are they're different, then these two objects cannot be homotopically equivalent. So this is something. So here is another interesting consequence that if we have a compact Lie group and a closed subgroup, which is not necessarily connected, and suppose that G and H naught are both semisimple, and with G mod H is 7, then yeah. So if either, so you have this extra condition, then the number of simple factors and number of simple factors of G is same. So this is a result which is also obtained by Gorbatchevich back. So let me. So these are the results. Like this is a computable description. But the moment you go beyond 4, the complexity increases. So it becomes non-tractable as far as we are concerned. So let me just talk about the steps in the proofs of this theorem. So
you have a couple of minutes.
Okay. So the point is that we have this classical way to look at the cohomology of G mod H, but also there is another way which is also not so recent, but it is the Cartan theorem. So Cartan theorem, it's a technical theorem which describes the cohomology of homogeneous spaces in certain, I cannot describe it now. So this goes into the proof. So it gives an alternate description for the cohomology of homogeneous spaces, and we have to modify it a little bit to suit our purpose because they assume H is connected, and then we have to do a lot of analysis with breaking up the spaces G and G mod H and a careful, very subtle analysis to obtain this formula. And stop now.
So the reason why you can compute the third and the fourth cohomology is related to the fact that for any simple Lie group, simple Lie algebra, you have a degree 3 element in this cohomology.
Say it again, please.
So I want to understand why the degree 3 and the degree 4 is computable, although above that degree it is not computable. Is it related to the fact that for any simple Lie algebra G, you have a degree 3 element in the cohomology of
like so there are this killing forms which gives
Yeah,
integer
yeah, yeah,
forms.
yeah.
So if you take higher forms, then the complexity increases.
Mhm.
The entire thing is broken up into pieces, like, you know, and
Mm.
that becomes extremely non-trivial.
But if you, for instance, like for degree 5, like if you look at these, I think for degree 5, you can like split into two cases, like the factors with with of type A and different
Yeah, I mean,
version, then
but yeah, if
different
you
ones,
look at,
then can
our
you
proofs, then you'll realize why it becomes complicated. There are
thank you,
certain, I mean,
purpose related.
yeah,
Let us
talk
discuss
later.
later.